IBM has just announced a massive breakthrough in the semiconductor world, unveiling the world's first ever Sub-1 nanometer chip technology. They have pushed transistor architecture all the way down to the 0.7 nanometer, or 7 angstrom, node. This tech allows us to pack a staggering 100 billion transistors onto a single chip no bigger than your fingernail. That is nearly double the density of the 2 nanometer chip IBM revealed back in 2021. To understand what this means for the next generation of chips and the engineering magic IBM used to make it happen, let's dive into the details right here on Technoverse. IBM claims its new chip delivers either a 50% performance boost or a 70% energy reduction, representing a monumental leap in hardware efficiency. If a manufacturer decides to supply the exact same amount of electrical power to this new chip as they would a current 2 nanometer chip, the device will deliver 50% more processing power. On the flip side, if they choose to cap the performance output so it computes exactly on par with that 2 nanometer chip, it will draw 70% less electricity. So how did IBM actually achieve this massive density? The secret lies in a completely new 3D transistor architecture called NanoStack. To really understand how revolutionary this is, we have to look at current technology. In modern chips, the two main types of transistors that make up basic logic gates, the N-type and P-type, are placed side by side horizontally across the silicon. This takes up a lot of valuable surface area. And it is important not to confuse this new tech with 3D packaging, where manufacturers just stack already finished chips on top of one another. NanoStack changes the game by physically stacking the N and P transistors directly on top of each other at the microscopic level, using a process called 3D sequential integration. Think of it like taking a sprawling single-story house and turning it into a 2-story duplex. You get the exact same amount of living space, but you cut the physical land footprint right in half. But the main advantage here is actually how the electricity moves. Instead of the current only being routed horizontally across a flat plane, the electrical signals can now pass directly up and down vertically between the stacked transistors. This drastically shortens the physical distance the current has to travel, eliminating bottlenecks, making the data transfer incredibly fast, and significantly reducing the energy lost along the way. Now, let's take a step back and look at where we really are, because there is a huge difference between a lab breakthrough and a chip you can actually buy. Has IBM built a fully functioning 100 billion transistor consumer CPU using the 0.7 nanometer node yet? No. What they have done is successfully built and validated the foundational building blocks. In the lab, IBM engineers successfully tested the ultra-thin bonding, the dual-channel engineering, and built working CMOS inverters, which are essentially the heartbeat switches of a chip. They also proved this 3D stacking can shrink SRAM memory by 40% in new research presented at the VLSI Semiconductor Conference. So, IBM proved that the physics, the materials, and the NanoStack architecture actually work in the real world. They successfully built the bricks, but now the rest of the industry, specifically massive manufacturing foundries like TSMC, Intel, and Samsung, has to figure out how to mass produce the skyscraper. So we are officially entering the angstrom era, where the components inside our computers are literally approaching the size of individual atoms. Because IBM is primarily an R&D powerhouse, they won't manufacture these chips themselves. Instead, they expect major foundries to adopt this 3D NanoStack technology and scale it up for commercial production within the next 5 years. The race to the sub-1 nanometer level is here. What do you think about IBM's vertical NanoStack architecture? Let me know in the comments below, drop a like if this helped you understand the tech, and subscribe for more deep dives.